Hey everyone, Ari here, working on worksheet number 11. And so I know we have a test coming up, so very critical to understand all this information. And yeah, let's get started. So the first one says write in symbolic language and negate, and this is the only problem that we were told specifically not to do in class, as this is pretty much review from stuff that was on the last exam. So here, this first one says that if a square root is not a natural number, then it is irrational. So we need some square root of a number that isn't natural. So let's say square root. Of course, the pencil will start acting up immediately. Square root. Let's try one more time. Square root of r. And what do we know about the square root of r is that it is not natural. So it's not contained in the set of naturals. And we have this if-then form. And that screams out to me that we want an implication. So the square root of r being not natural implies that, the square root of r being not natural implies that the square root of r, that it is irrational, meaning the square root of r is irrational, meaning it's in the set of r minus q. It's a real number that is not rational. That's what this r minus q means. And the one thing that I actually had a disagreement with Professor Carbone about in class that maybe some of you noticed is that we do have to define where this r comes from. And when it's not specified, we just, the problem just says a square root. It doesn't say a square root of a natural number. It doesn't say a square root of any particular type of number. So the takeaway for the sake of this class is that if a variable is not specified, we're going to just assume that it's a real number. So we're going to say r in the reals. So for some r that's a real number, the square root of r is not natural implies that the square root of r is irrational. Not natural implies irrational. And so now we want to negate this statement. And before we negate it, let's write it in a different form. So we know that implications could be written in the form of not p or q. And if you need to go over that again, I talk about this in a video of why this form is equivalent to the if-then statement. And we definitely learned about this in lecture. So definitely go back into the lecture slides to understand this better if you don't recall. Now, here's the really tricky part of this problem. Usually when we have an implication, the entire left-hand side is p and the entire right-hand side is q. So that's the temptation, is to negate this entire part over here. And the important thing that we need to keep in mind here is that actually that first part, r being a real number, is not part of our statement. That's almost like a prerequisite to our statement, or a preamble. It's not actually stating anything, or it's not stating anything of real substance. So the important thing to remember here is that we're not negating that first part, which is r is contained in r in the real numbers, and now we could start negating. So not p means that the square root of r is contained in the natural numbers. Square root of r is natural, or r, and this part of the statement is staying the same, r is in r minus q. The square root of r is in r minus q, and we could put all of that in parentheses if we want. So this is our alternative form of the implication. And now when we negate this, it's going to be pretty easy, where we're going to say, one thing that I totally botched, sorry about that, is we have to put a quantifier. We have to say for all r. So that was my bad. And also over here, we should be saying for all r. So sorry about that. So now when we negate it, say there exists an r in R such that we have the square root of r is not a natural number and the square root of r is a rational number. And you could also say is not an irrational number. You could just go like that and write it like that. I would rather state it in the positive just because I think it reads a little bit nicer, that r is a rational number. So the negation again is that there is some r such that the square root of r is not natural and the square root is also rational. Not natural, but it is rational. And you could see how that is the antithesis of our original statement, where we're saying that basically any square root that's not natural has to be irrational. Now we're saying, no, there's an example where it's not natural, yet it is rational, or it is not irrational. And I feel like the fact that the words natural and rational rhyme makes this so confusing to talk about, at least for me. I'm like confusing myself talking about this, but hopefully that helps clarify some things about that problem. And one other thing to note is that in Professor Carbone's solutions, she specifies that the universe of real numbers that R belongs in has to be greater than or equal to 0. I don't agree with her on that, and we sort of hashed it out in class, but I still don't agree with her. And her reasoning for that basically is for any real number that's less than 0, or R in this case, is always going to be irrational. So it's like, it's not really useful. She referred to it as a vacuous statement. It's like a statement that doesn't say anything. Like the square root of any negative number is irrational. That's true, but it's always true. So we don't really need the if part of the statement. We don't really need P to say that that's true, which I agree with all that. I still think that the way I wrote it is better and more general. So I'll let you guys decide what you think. Okay, so we're going to use the color green for part B. And this one's a little bit simpler, I think. Primes have irrational square roots. So, and we're not talking about just one prime. We're talking about all the primes. So for every P that's in the primes, we have irrational square roots. So the square root of P is irrational. And I think another way of saying this, or for every P that's in the primes, square root of P is not rational, like that. I think that's also equally correct. And honestly, I like to write it this way. We talked about in class how you could write this to be irrational. I'm pretty sure the second way that I wrote is also correct. But either way. And then when we negate it, this one's pretty straightforward. Negating it would be there exists. Remember, for all becomes exists. Primes in P, the square root of P is rational. So the negation of the statement is that we could find at least one prime. There exists some prime where the square root is rational. And that would negate the statement that all primes have irrational square roots. Hopefully that makes sense on a logical standpoint and also the notation here. All right, now we get to the fun. We'll use yellow. So number 2 says, prove by contradiction that 2 times the square root of 5 is irrational. I'm going to use the proof that involves prime decomposition because it makes more sense to me. And I understand the odds and evens proof, I guess, that second proof that we learned, but you're never going to be asked to use one specific method of proof or the other for this type of problem. it's going to be up to you which proof you want to use. So I just prefer to use the prime decomposition proof, so that's the one that I'm going to walk through right now. So we want to prove by contradiction. So if we're proving this by contradiction, that means that we have to actually assume that 2 times the square root of 5 is rational. So I'll start writing it out. One thing that doing this on an iPad allows me to do is write out full proofs, basically. For the sake of contradiction, suppose 2 times the square root of 5 is rational. That is, what does it mean for something to be rational? It means that it has to be able to be expressed as a proper fraction. Yeah. Actually, well, it could be an improper fraction. It doesn't matter if it's proper. It can't have a denominator of 0, and it should be in simplified form, which is kind of related to the second method of proof. But anyway, that is 2 times the square root of 5 equals a over b. And what are the restrictions on a and b? For some a and b, we'll say that they're integers, and b cannot equal 0, right? If b is 0, then a over b becomes not kosher, I guess. It becomes something that makes our heads explode in math. So we don't want that. So we want b to be some non-zero integer and a to be some any integer. Okay, so now let's do some algebra here on this thing. So we'll square both sides. And 2 times the square root of 5 squared, we square the 2 becomes 4. The square of the square root of 5 is 5. So we get 20 equals a squared over b squared. And 20b squared equals a squared. And this is kind of where we need to recognize what's going on. So we want to focus on prime decomposition. That's the method of proof that we learned, the first way that we learned to solve this type of problem. And if you remember, there was the last worksheet we did, we had this problem that said like n equals m squared, where m is a natural number, and you have to prove that n has an even number of prime factors. And the way you prove that is by showing that m has some number of prime factors. So m squared has 2 times a number of prime factors, which is an even number. And since it's m squared is equal to n must also have an even number of prime factors, because numbers that are equivalent have the same number of prime factors. Okay, so that's kind of the motivation. So using that same logic, a squared has an even number of prime factors. And the way to write this out properly would be prime factors of a equal p1, p2, pn. So a squared equals p1, p2, pn times p1, p2, pn. And you could see that this is an even number, I think, because all of them have pairs. So the number of prime factors equals 2n. Hopefully that's clear, which is even, because we know that n is a natural number. So we know that a squared has an even number of prime factors, and I'm not going to write it all out just because I don't feel like it, but b squared, we can make the same argument with b squared, and when you do write out this proof, just make sure that you don't use p, use q or something, and don't go up to n, go up to like t. So set b equal to like q1, q2, qt. It's just good practice to use different variables, different values and it's even better practice if you specify that Q is prime. And yeah, that's even better. And I should have specified that with the P's, that each P is a prime. And so here, the B squared is going to gives us 2t prime factors. But we also have this 20. And 20 equals 5 times 4, which equals 5 times 2 times 2. This is the prime factorization of 20. So equals 3 prime factors. So if we're counting prime factors on both sides of this equation, we have 2t plus 3 on the 20b squared side equals 2n on the a squared side. And this is where we run into our contradiction. And this side is odd, that side is even. But we said that 20b squared is equal to a squared, which means they represent the same number. And if they really did represent the same number, it would be impossible for them to have a different amount of prime factors. That's the point. The point is that we've just shown that they have a different number of prime factors, which should be impossible because they're supposed to represent the same number. So this sort of concludes our proof by contradiction, and it's sort of a roundabout way, but we prove that 2 times the square root of 5 is indeed irrational. It can't be expressed as this fraction because the implications of this fraction end up being that odd equals even, or 2t plus 3 equals 2n, where n and t are both natural numbers. So yeah, cool. All right, number 3 I think confused a lot of people, including myself when I first looked at it. So let's just start off. I'll just read through it real quick. So we're going to construct a sequence of primes p sub n given by the recursive rule p of 1 equals 2. So we'll just write that one down. The first prime is 2. And for all the subsequent primes, for n greater than 1, we're going to define the next prime. P of n plus 1 kind of represents the next prime to be the smallest factor of the product of all the previous primes plus 1. So let's figure out how we're going to find P2. P2 is the product of all the previous primes plus 1. And then we're going to find the smallest prime factor of that. So the previous prime, there's only one previous prime, and that's right over here. That's 2. So we have 2, and we can't multiply it by anything because there's no other primes. So that's our P1. And we don't have a P2, P3, Pn yet. So we just have 2 plus 1, which equals 3. And now we have to ask ourselves, what is the smallest prime factor of this number 3? The answer is 3. Easy enough. So now P3. P3 is the product of all the previous primes that we came up with, meaning 2 and 3. 2 times 3, and that's all we have. So now we'll add our 1, which gives us 7, and the smallest prime factor of 7 is 7. P4, same thing. 2 times 3 times 7 plus 1, that equals 43. And 43 also happens to be prime, so the smallest prime factor of 43 is 43. Now this one's going to get really wonky. P5, and this gets out of hand pretty quick, so we're going to stop at P5. But P5 gives us 2 times 3 times 7 times 43 plus 1, which equals 1807. And the reason we learned how that division algorithm for all the different single-digit numbers, like you could look at a number and tell if it's divisible by 3 or divisible by 9 if you follow these certain rules. We learned it so that we could better identify if numbers are prime. Now, problems we run into are that some things are divisible by 2-digit numbers, but not by 1-digit numbers. And 1807 is a good example of that, where I don't know if there's a trick to know this, but it happens to be equal to 13 times 139. And so the smallest prime factor of 1807 is 13. So I'm not going to actually do P6, but just the way we would construct it is 2 times 3 times 7 times 43 times 13 plus 1, and then find the smallest prime factor of that number, and it's going to give us a new number, and that number happens to be 53. So basically every time we follow this recursive rule, we're going to produce a new prime number, and we can do this infinitely many times. This is the rule that kind of exemplifies that there are infinite primes. All right, awesome. So now we are on to the next worksheet, and this one's only just a standalone problem, all by itself. And I'll go back to blue for this one. Have I used blue? I used a little bit of blue, but not enough. There's only a few colors that I really like to use. Like, I have red. I just don't like the way it looks that much. I don't know. Maybe you guys could suggest other colors. So for number 4, we want to prove that if for some n in z greater than 1, meaning some integer n, 2 to the n minus 1 is prime. So we have 2 to the power of some integer that's not 1. And this is going to give us a prime number. Then n has to be prime. And we could just try plugging in a few numbers. Like let's plug in, we know that 2 is a prime number, so let's do 2 squared minus 1, that's 3, which is prime. Then n is prime, and n is 2 in that case, so that works. What if we plug in 3? 2 to the power of 3 is 8, minus 1 is 7, so that's prime, and 3 is prime. So first couple of examples that I could think of definitely work. And in this problem, we're actually given a hint. So the hint says let x and n be integers greater than 0, and let, I'm going to reorder this, n equal lk, where 1 is less than L and K, which is less than N, meaning L and K are not N and 1 respectively, or 1 and N respectively. They're two numbers, meaning N is composite, basically. N is composite. So this is just part of our hint. This is not part of our problem, because in our problem we said that N is prime. So if this is the case, if we have this composite n that's positive, then we could say, x to the n minus 1 is equal to x to the l minus 1 times x to the l times k minus 1 plus x to the l times k minus 2 plus x to the l plus 1. And this 1 is like x to the l times k minus k, which becomes x to the 0, which becomes 1. So x to the l times k minus k. That's just a little explanation of how we end our sequence like this, why we end our sequence with x to the l plus 1. All right, so this hint is not just a hint for how to solve this problem, or I should say it's not just giving us this equation for no reason. It's basically telling us that it's giving us this hint that embeds an n that is composite. And in our problem, n is prime, so why would we be getting this hint? Maybe we're supposed to do a proof by contradiction, where we're actually going to suppose that n is not prime. So let's try that and see what we come up with. But hopefully you understand like how that hint indicated to me This is like a little bit of a test-taking trick. Seeing that hint indicated to me that we're supposed to do a proof by contradiction here. And you guys know that I have a strong bias toward proof by contradiction anyway. And yeah, debating what color to use. I'll go back to white for the proof by contradiction. So for the sake of contradiction, suppose, what do we want to say? For the sake of contradiction, what are we going to say here? That we're going to keep our premise the same, but we're going to flip our conclusion. That's what we do in a proof by contradiction. So we're going to suppose that 2 to the n minus 1 is prime. That's our premise. And we could say for n in z greater than 1, although I don't want to bog us down in the details too much. So 2 to the n minus 1 is prime. And n is composite. Bam, exclamation point. This is for the sake of contradiction. So if this is the case, if we have this composite n, we see in our hint that when we have this composite n, we could do this x to the n minus 1 equals this whole thing. So since n is composite, n equals lk. I'm just going to use the same variables to make it easier. For L and K that are, what do we know about n? That's a positive integer. So I guess we could say that they're integers, or we could even say that they're natural numbers, because they have to be between 1 and n, not inclusive. So and 1 is less than L and K, which is less than n. Not less than or equal to, because then we could still have n being prime. And we want to say that n is composite, so that's why it's strictly less than. Okay, great. So now, the formula that we're given here is this x to the n minus 1. And here we're clearly using a base of 2, because we have it right here. So let's just try this out and see what happens. We have 2, oh baby, okay, 2 to the n minus 1 equals 2 to the L minus 1 times 2 to the L k minus 1 plus 2 to the L k minus 2 plus 2 to the L plus 1. And I explained earlier how we get these terms at the end there. We're just going to keep subtracting from k, and eventually we're going to get k minus whatever 1 minus k is for that term, and then we're going to get k minus k for that term. Wicked. So what do we know about this problem? We're saying that 2 to the n minus 1 is prime. That's important. If we have a prime number or some expression that is prime, that means that the only factors for it, so its factors are 1 and 2 to the n minus 1. And here we're saying, here we have the factors 2 to the L minus 1, and this long expression over here, 2 to the L k minus 1 plus 2 to the L k minus 2. We have this long expression. So basically the only way for 2 to the n minus 1 to be prime is if either 2 to the L minus 1 is equal to 1 and this long expression is equal to 2 to the n minus 1. So I should write this out. Either either 2 to the L minus 1 equals 1 and 2 to the L k minus 1 plus 2 to the L k minus 2, all that stuff, equals 2 to the n minus 1. And that way the product of this times this equals 1 times 2 to the n minus 1, which is equal to 2 to the n minus 1, and the equality over here, this equation makes sense. Or, and I'm going to give myself a little space so that I could write in between, 2 to the L minus 1 equals 2 to the n minus 1, and 2 to the L k minus 1 plus 2 to the L k minus 2, yada yada, equals 1. And one thing to note is that there's a plus 1 at the end of this, which means that all of this part, excluding the 1, would be equal to 0. That's just something to notice. So there's a lot of reasons these things can't work. Let's talk about it. So I'm going to choose to just explore the expression 2 to the L minus 1 because it's just a lot simpler to work with. This first expression implies that 2 to the L equals 2, which means that L equals 1, right? 2 to the power of 1 is the only power that will keep it equal to 2. And, okay, that's interesting. So either we have L equals 1 here, and here, this means that L equals n, right? Because it's the same exact expression, just with these different variables in the exponent, so these exponents have to be equal to each other. I don't think I need to do any more algebra to show you that. I think we could all see that pretty loud and clear. And we know that n is equal to lk, so this would imply that up here, k is equal to n, and here, k is equal to 1. Right, because we need 1 times L, or k times L equals n, and if L already equals n, then k has to equal 1. That's the second case. And in this first case, we have L is equal to 1, but L times k is equal to n, so k must be equal to n. Whew, all right, that was a lot. So this is where our contradiction is. Earlier we said that n is composite, meaning it has these factors lk, where they are strictly in between 1 and n, meaning neither of them are equal to 1 and neither of them are equal to n. But then when we looked at the implication of that, when we started doing this expansion, this whole thing, we basically realized that in order for 2 to the n minus 1 to be prime, L and k had to equal 1 and n, or n and 1, respectively. So, meaning n actually had to be prime. So, I guess the way I would conclude this proof is by saying, therefore, n is not composite, and we have a contradiction. All right, that was a lot. 4 problems, and the last couple were definitely tested us and made us do some work. So anyway, good luck this week in your studying, and I'll be available through GroupMe, through email, through the comment section on the YouTube video. If you guys have any questions at all about this material or other material, homeworks, anything like that, please feel free to reach out. And yeah, good luck with everything.